A median of a triangle is a line segment that has its endpoint, a vertex of the triangle, and the midpoint of the side opposite that vertex. For instance, in the triangle ABC, the point M is the midpoint of the side BC. The segment AM is a median of this triangle. If we find the midpoint N of the side AB and join the point C and the point N, we have another median of this triangle. Obviously, these two medians are intersecting at a point denoted by O, for instance. A more surprising fact is that if we join the point B and O and extend this line to intersect the sides AC, and we denote this point as P, then P turns out to be the midpoint of the sides AC. In other words, BP is the third median of this triangle. In this video, we're going to study this awesome fact, as well as some other interesting properties and consequences surrounding this phenomenon. To kick off the study, we will establish the following lemma. The intersection of any two medians of a triangle is at 2/3 the way from a vertex to the opposite midpoint. The figure illustrates this lemma. Suppose AM and CN are medians of the triangle ABC, and they intersect at the point O. The claim is the ratio of AO to AM is 2/3, and the ratio of CO to CN is also 2/3. To prove the claim, the first move is to join the points N and M, since both of them are midpoints of the corresponding side. According to the basic proportionality theorem, we have the following two facts. 1. The line NM is parallel to the line AC. 2. The length of NM is 1/2 the length of AC. Meanwhile, since NM is parallel to AC, according to the alternate interior angle theorem, the angle MNO is in fact concurrent to the angle ACN. Also, as a pair of vertical angles, the angle NOM is concurrent to the angle COA. Therefore, by the angle-angle similarity criterion, the triangle ONM is similar to the triangle OCA. Thus, the ratio of NO to CO is equal to the ratio of MO to AO, which in turn is equal to the ratio of NM to CA, which was shown to be equal to 1/2. Finally, we can compute the ratio of AO to AM by first of all recognizing that AM is equal to AO plus OM. However, AO is just a double of OM. Hence, we could cancel the OM from both the numerator and the denominator to end up with 2/3 as the numerical result. And similar arguments could be applied to the ratio of CO to CN and concludes the same number. And this completes our proof of the lemma. Now we come to the main theorem. Let's state the theorem formally. The three medians of a triangle are concurrent at a point called centroid. With the help of the lemma, the proof becomes rather simple. Suppose the median AM intersects the median CN at the point O, and the median AM intersects the median BP at the point O prime. By the lemma, we must have AO to AM equals 2/3, while AO prime to AM equals 2/3 as well. In other words, both O and O prime are at 2/3 the way from the vertex A to the opposite midpoint M. Therefore, the point O and point A must be the same point. By construction, point O is on both AM and CN, and point O prime is on both AM and BP. Since these 2 points are in fact the same point, therefore, this point must be on all 3 medians. In other words, this point is the so-called centroid. And this completes our proof of the median concurrence theorem. To practice on the concepts we have introduced in this video, let's work on the following example. In the figure below, point M is the midpoint of the segment BC in the triangle ABC. Additionally, point N1 is the centroid of the triangle ABC. Point N2 is the centroid of the triangle AMB, and point N3 is the centroid of the triangle AMC. Problem 1. Show that points N1, 2, and 3 are collinear, which means they are on the same line. Problem 2. Show that line segments N2, N1 and N1, N3 are congruent. To prove problem 1, let's consider N2 and N3 in the context of the median of some triangle. For instance, let AM2 be a median of the triangle ABM and AM3 be a median of the triangle AMC. Then, by the lemma, we have the following relation. AN2 to AM2 is equal to AN1 to AM, which is equal to AN3 to AM3, because all 3 of them is equals to 2/3. Therefore, from the basic proportionality theorem, we must have N2, N1 parallel to M2M and N3, N1 parallel to M3M, in which we think of N2, N1 as a line segment cutting the triangle AM2M, and we think of N1, N3 as a segment cutting the triangle AMM3. Since both N2, N1 and N3, N1 contain the points N1, and both of them are parallel to the line M2, M3, these 2 lines must in fact be the same line, because in Euclidean geometry, there is only one line through a given point parallel to another given line. And that's how we prove that those 3 points are collinear. As for problem 2, By corollary of the basic proportionality theorem, n2 n1 must be 2/3 of m2 m. At the same time, n3 n1 must be 2/3 of m3. But since m2 is the midpoint of bm and m3 is the midpoint of mc, we must have m2m equal to a half of bm, and m3m is equals to a half of cm. However, m is just the midpoint of bc. We must have bm equal to cm. And this string of equalities leads to the conclusion that n2 n1 and n3 n1 is just the same. And this completes our example. And thank you for watching. I'll see you next time.